Good morning, folks. This is tutorial number 13, and it's the continuation of what I did in tutorials 10, 11, and 12 in this playlist. I refer to it as strategy 3 because what I will do is I'll repeat the same problem, except that I will use something called rigid connection for the place where the concentrated force is applied. So the problem that we have done in 10, 11, and 12 is this. And in 10, I basically created a line AB and I put the load right in the middle of it. And then in 11 and 12, I created three lines from A to the middle point to the B, and B all the way to C, and then create a connection. In tutorial 11, I made a connection or what is called a connector, a welded connector where I placed the concentrated force, and a hinge connector where the internal hinge exists at the point B. In tutorial 12, instead of using the weld connector, I used the tie option to put the two pieces, left line and middle line, together, and then of course it's going to be a hinge at the point B. Right now, I'm going to do, instead of a tie or a connector, I will use a rigid connection to basically make AB one piece. Okay, so here's what's going to happen. I'll call this thing this as killing a fly with a cannon, because I mean the first one, obvious one, is the obvious one, but these tutorials tell you how some of these other important connections are used in other more complicated situations. So this is going to be a rigid connection, and this is going to be a connector where I make it a hinge basically. Now, the problem is out of Hippler's structure analysis textbook, and if I assume that the cross-sectional radius is 2.486 inches, it'll give you an I of 30 inch to the 4, which is used what is in the last three slides, and that is the analytical solution at the point B. So the way we assess whether we are doing this thing right or not, we look at the deflection at the point B based on an analysis or analytical solution. It should be around 4.58 inches downward. Okay, so here's my strategy. Three lines, left line, middle line, right line. Concentrated load goes there, and a hinge goes here. And this I make it a rigid connection. This one is going to be a hinge connection. And in 10, I showed you that whether I use hinge, join, or cylindrical connection, it'll give you the same answer, but I will use hinge. Okay? So don't join anything, because you want to have duplicate nodes at these points. And to do that, we make sure that we don't join anything. And also when we measure it, we have this thing off so that there will be duplicate nodes. Okay. I will not do in this tutorial. I'm not going to do join and cylindrical. I'll just use hinge connector right there. So let me remind you that when we use hinge connector or the other ones, which we're not doing in this one, in this tutorial, you need a local coordinate system. And actual directions of this is important, but it doesn't matter where the origin of it is. In tutorial 12, I showed you that even if I had another coordinate system here, which had the same direction X, it will work, okay? All right. Now, this is the one that we're using. And there is the analytical solution using the principle of virtual work. And the answer should be roughly 4.58 inches. Good. So let's go ahead and do that. I start with a part file. So I'll create three lines. I can do this whole thing in a sketch, but I'd rather do it as a wireframe. So essential, a line, point and direction. The point I'm going to make, 0, 0, 0. Direction is Y, 12 feet. Mesh, or say okay, mesh, 12 feet. Another line, same story, from this point in the Y direction, again 12 feet. And the last one is going to be 15. So another line between this point direction y, the only difference is that's going to be 15 feet. Okay, so I've got all these things worked out. Now I'm going to make my coordinate system, and coordinate system, as I said, it doesn't matter where you put it. If you want to put it somewhere off, no problem, but I'll put it right where it's supposed to be, right there. So here's the axis system. If you don't do that, at some point you're going to have to come back and create a coordinate system, because the hinge, you cannot, basically it's not, you have to specify the direction, the axis system. Okay. Good. Now we're going to create our material. So I go to view tools, create a material, or call it steel tutorial 3, tutorial, sorry, 13. Okay. It's going to be creating the database, but of course there's no numbers here. We're going to take this thing and put it in there and input the numbers. So we go there, we go to our material table. Under structural, abacus multiphysics, mechanical, elasticity, elastic, 29,000 KSI, 29,000 KSI, and Poisson ratio 0.3. And then we say OK. So now we're going to do the meshing. So we go to structural model creation, empty FEM, select the mesh tab, beam measure, make sure this thing is off, remember, and element size is 1 foot. So there's going to be 12 of them over there. And repeat this thing for the other lines. This is off, right? So there will be duplicate nodes there. This one is going to have 15 elements, which is fine. Now, cross-sectional information, properties on their profile. It's going to be circular and 2.486. I'm pretty sure that's what it was. 2.486, good. And then inches, don't forget the inches. Don't want it to be foot. Okay, good. So that takes care of this, and now the cross section, beam sections. So we can select all 3 of them at the same time and use the profile wall 1. And we can close it without selecting orientation, because it is actually a circular cross section. Doesn't need orientation. All right, that takes care of this. Now we're going to create our connections. So connections, first one is going to be the rigid one, rigid. And I'm going to select for the first support the end of this line, and then for the second support the end of that line. And to make sure that there are no mistakes, so I'm going to hide this. For the first support, I select this. For the second support, I'm going to go to the hiding, select that point. Okay. So a connection has been created here. A rigid connection, yeah, a rigid connection has been created here. And then I'm going to create a connector here, which is going to be hinged later on in a minute. So go scroll, here's the connector. Once again, first support is going to be this point. Second support, the end of the line that's in hiding, which is this point. Yep. And then this is going to be hinge. Hinge. And notice that you have to select the coordinate system here. So let me go to the show mode, and there is my coordinate system, axis system. It's lined up in the x direction, and this is what that's what we need for releasing the moment about the x-axis. So we say okay, that's pretty much done. Now we're going to apply the boundary conditions. Of course, what we need to do is we have to switch to the structural scenario creation. Select the FEA model, find it on the model mesh, and then make sure it is, for procedure, it is static perturbation. Good. Clamp the end, left end. So on the boundary conditions, you can clamp this side, okay, and then roller on this side, on the right side. So fix displacement, that, oh, not the whole edge. Remove this, just this point. Uh, does not move in X, does not move in Z. It can rotate about X-axis and Y-axis, no problem. So this becomes a roller along the Y direction. Now we're going to apply our load. So we go to loads. Let's use a force and we can apply it to that point. Because these are rigidly connected to each other, these two vertices are rigidly connected, it doesn't matter what we picked. So it's going to be minus 8K kilo pounds, 8,000 pounds. And then there's a concentrated moment at the other end. So we apply a torque at that location about the x-axis, and it's going to be minus 30,000 pound-foot. Okay. Hopefully we haven't forgotten anything, and let's go ahead and check first of all for model and scenario. If there is any obvious mistake, it's going to pop up. Nothing there. And we can do a simulation check. I don't anticipate any issues here. Seems to be going through. Successfully checked. And finally, we're going to run it. The displacement at the hinge better be 4.58 inches downward. Otherwise, we did something wrong, or I did something wrong. Okay, it's almost done. Displacement 4.58. Great. And the pattern, of course, is correct. And that takes care of this tutorial, which we did it based on a rigid connection here and a connector which was a uh, hinge. Okay. Oh, yeah. Before I actually stop this, let me go back. Instead of here doing a vertex to vertex, not at the hinge, but at the rigid, instead of doing vertex to vertex, vertex to vertex, let me do the whole edge to the whole edge. Let's see what happens. So I go back to my connection here, rigid connection here, right there. This one, right? Double click, remove the support. Actually, you know what? Let's go first of all to the model so that we can see stuff. Right. And do the same thing. Double click on the rigid connection. Remove the support. Remove all. So what I'm going to do is for the support one, instead of taking the end of the line one, I'm going to select line one. And for the support two, I'm going to select line two. Line two is in hiding. That's why I can't pick it from here. It's right there. I mean, if you want, I can bring it there. I already picked it. Good. So let's go and run it and see what happens now. Notice that it did create a rigid connection between this line and that line. Let's see what happens. When I run it, what happens? My guess is that nothing is going to deform because this rigid connection means these two are rigid things attached to each other. So will it run? May run, but should not get any stresses in it because it's rigid. So let's check first of all. No problem there. And now we're going to run it. and see what happens. Vertex to vertex makes sense, but the entire edge to entire edge being rigidly attached to each other, I mean, just doesn't sound right. So we'll find out. You see that? Just doesn't make sense. And in fact, if you look at the displacement, just, you know, it's just, now, yeah, that doesn't make sense. Okay. So once again, if you go and say vertex to vertex, it'll be fine, but not edge to edge. It just does not give you meaningful results. Good luck.